In this lesson, we're working on big idea number 2. How does the type of bond between two atoms determine the physical and chemical properties of a compound, specifically focusing on learning target number 6. If given the name or the formula of a compound, can you determine if it's an ionic, polar, or nonpolar compound and predict its properties based on the intermolecular forces it can make? Ionic and covalent bonds transfer or share electrons so that atoms in a molecule become stable. Once a molecule or ion is stable, it can still have electrostatic attractions to other stable molecules. The force holding two or more stable molecules or ions together are known as intermolecular forces because they're between molecules. Intermolecular forces are the primary influence on a compound's physical properties. The stronger the intermolecular force a compound can make, the higher its melting point, the more likely it will be solid at room temperature, and the harder the substance will be when it's a solid. All three of these physical properties depend on how easy it is to separate one molecule from another by breaking its intermolecular forces. The strength of the intermolecular force is dictated by how great the charge difference is between the two molecules. The strongest intermolecular force is known as an ionic force or an ionic bond, where you have a full charge attraction between cations and anions. Sodium chloride is an example. If I draw the Lewis dot diagram for sodium and chlorine, I'm going to get one electron transferred between the two elements. Chlorine's going to have a full 1 minus charge, and sodium will have a full 1 plus charge. Because chemicals exist in 3 dimensions, sodium can actually attract more than one chlorine. In a sodium chloride crystal, every sodium ion is completely surrounded by chlorine ions. I can even put one in front of the screen and behind the screen in order to make a 3D cube. Now every chlorine is attracted in all 6 sides by sodium atoms as well. And the crystal can grow as long as you supply it with the appropriate ions. The full charge attraction between each sodium and each chloride is known as an ionic bond or an ionic force. Let's jump down to the third strongest intermolecular force, dipole-dipole forces. It's a partial charge attraction between opposite ends of two polar molecules. Simplistically, it can be shown like this, where I have one polar molecule with a slightly positive end and a slightly negative end, attracted to another polar molecule, but they orient themselves so that the oppositely charged ends are facing each other. Because I have two polar molecules, also known as dipoles, attracting each other, this is known as a dipole-dipole force. It is not as strong as an ionic force because here I'm using partial charges instead of full charges. Here are some examples using real molecules. A simple example would be hydrogen chloride. Here's the stick diagram for HCl. This is a polar bond where chlorine is more electronegative, so it will receive a partial negative and hydrogen will receive a partial positive. If I copy that diagram, you can see the slightly negative on my first chlorine will attract the slightly positive on the second hydrogen. Molecules can be more complicated as well. For example, here's a diagram for CH3I, another polar molecule. The I is more electronegative, so it receives a slightly negative, and the C is slightly positive. This is a polar compound because if you look at the overall structure, it passes the line test. If I have two CH3Is, the molecules can attract each other using the slightly negative on one I and the slightly positive on the carbon on the neighboring molecule. Because I'm using partial charge attraction, this is a dipole-dipole force. Hydrogen bonding is a stronger force than a dipole-dipole. It's actually a special type of dipole-dipole with molecules containing specific elements. A hydrogen bond is a strong partial charge attraction between two polar molecules containing HF, HO, or HN bonds. It's important to remember that the H needs to be directly attached to an F, O, or N in order for hydrogen bonding to occur. It's also important to remember that both compounds need to be polar in order to hydrogen bond. Here's a simple diagram representing a hydrogen bond, where we have one polar molecule with a slightly negative end and a slightly positive end created by having an H. On the neighboring molecule, we have a slightly positive end and a slightly negative end, but that slightly negative end is created by having an O, an N, or an F. Each of these elements contain a strong, slightly negative, and the hydrogen a strong, slightly positive. It's not quite a full charge, but it can get pretty close. HF, HN, and HO are the most polar bonds that are possible because they have the greatest electronegativity difference without becoming an ionic bond. Hydrogen bonding is found in nature quite prevalently, and it's very important. It's what makes water a liquid at room temperature. It holds two strands of DNA together, so it's given its own special classification. Here's an example of a real compound that hydrogen bonds. Here's the stick diagram for hydrofluoric acid. This is an extremely polar bond, with fluorine having the larger electronegativity difference. If I have two HFs, the strong partially positive H on one molecule is attracted to the strong slightly negative F on the neighbor. This is known as a hydrogen bond. The weakest intermolecular force that we'll discuss in our course are London dispersion forces. There are attractive forces between the positive nuclei of atoms in one molecule and the electrons in a neighboring molecule. The larger the molecule is, the greater the London dispersion force attraction. Here are two examples. Here's the stick diagram for an oxygen molecule. Because these two elements are the same, there's no electronegativity difference, so this is a complete nonpolar bond and no partial charges. If I have two oxygen molecules, you can't dipole-dipole or hydrogen bond or ionic force. But the protons in the nucleus of one oxygen are attracted to the negative electrons on the neighboring molecule. This is a pretty weak attraction. The larger the molecule, the more protons and electrons you have, which means the stronger the London dispersion force. Here's a more complicated example. CF4 is a molecule with polar bonds, but they cancel out, so it's a nonpolar compound overall. Fluorine is more electronegative, so each F carries a partial slightly negative, and the carbon slightly positive. But this molecule is symmetrical, or I can't draw a line separating a positive side and a negative side. So it's a nonpolar compound overall. If I have two CF4s, I cannot dipole-dipole because the arms, the fluorines, have the same charge. But the protons in this fluorine can be slightly attracted to the negative electrons in this fluorine. This creates a London dispersion force. The LD attraction between two CF4s is stronger than the London force between two oxygen molecules, simply because there's more protons and electrons to cause an attraction between them. The chart on the bottom of the note summarizes the effect intermolecular forces have on the properties of compounds. Let's do ionic compounds together. Ionic compounds are made of a metal and a nonmetal transferring electrons and having full charges. A full charge attraction is known as an ionic bond or an ionic force. Because ionic forces are the strongest intermolecular forces possible, the melting point and boiling point of ionic compounds is really high. When you melt or boil a compound, you have to physically separate the particles or break the intermolecular forces holding the substance together. The stronger the force, the higher the melting and the boiling point. The stronger the intermolecular force, the more easily it is to hold the particles in a crystal, making the compound a solid. Because ionic compounds have a really strong ionic force, they are all solids at room temperature. And they're also very hard when they're solids. The ions are locked in position. They can't slide past each other very easily. Let's leave the property of conductivity until later. Try to fill the rest of the chart out on your own for polar molecular compounds and nonpolar molecular compounds. Determine what type of force that these things can make, and then predict whether the melting point or boiling point will be high, medium, or low, whether the state will be solid, liquid, or gas, or whether it will be hard or soft. Here are the answers. Polar molecules have slightly positive and slightly negative ends. That means that two polar molecules can attract each other through dipole-dipole attractions. Or, depending on if they have the right combination of atoms, if they contain a nitrogen, a fluorine, or an oxygen with a hydrogen directly attached to one of those, then it can form hydrogen bonds. Both of these forces are kind of medium strength. So polar compounds have medium melting points and boiling points. And they're usually liquids at room temperature. When they are in their solid state, they can be medium hardness, which means they are hard. You can't squish them, but you can carve them. Nonpolar molecular compounds have no charges or equally distributed charges. That means they can only have London dispersion forces attracting them together. Because London dispersion forces depend on the size of the molecule, the melting point and the boiling point are different depending on the size. Really small nonpolar compounds have really low melting points, but very large nonpolar compounds can have medium melting points. Also, depending on the size of the compound, nonpolar molecular compounds can be solids if they're really big, they could be liquids if they're medium size, or they can be gases if they're really tiny. In the solid state, nonpolar molecular compounds are very soft. In order to conduct electricity, a substance needs to have charges that are able to move. Ionic compounds have full charges, but as a solid, they are locked into position by really strong ionic forces. Therefore, as a solid, ionic compounds do not conduct electricity. When an ionic compound is melted or dissolved in water, the ionic forces are broken, allowing the full charges of the cations and anions to move. Therefore, they then conduct electricity. Polar molecular compounds have slight charges, so they can conduct electricity only a very tiny amount. Sometimes it's so small it's not detectable. Nonpolar compounds have no charges or equally distributed charge. That means that they don't conduct electricity. On the worksheet attached to this note, you'll find questions where you have to identify the type of compound, name the intermolecular force it can make, and then predict or compare properties.